Okay, well, welcome to the Computational Chemistry class. Thank you for your patience and dedication to go over different forms of rescheduling. So I think we are done with setting up times, and we may adjust place a little bit. So regarding times, there are right now 2 undergraduate students who are interested to take the class, but they have overlapped. They may arrive maybe 6:15, and I want to talk to them. Maybe we will keep things in books for 6, but everyone will arrive a little later. Because starting really later, like at 7, it is too much. Then we'll take time from the sleep. So, what is the class about? What are the goals? Well, most of you are already involved in some research, some theoretical and computational, some are involved in experimental, and you may broaden your horizons and add a paragraph or page or a chapter into your thesis or a paper made by another method. So we will make this course project-based, at least the grading project-based. And here is an example of what is done by students of the similar course last year. So you see some mini projects that take about 6-8 pages of written description, and it is application of the methods practiced in there will be lectures and lab methods practiced in the lab for some research projects. So if you can take it with you and take it as an example. If you can do something like this right now, you do not need to come to the meetings. And those we have in abundance. You are welcome to take them at home. There are some of the similar works from previous more years in the past, but I have limited supply. Please do not take them with you. What else? Oh. So please take one of the green sheets. I can show you. Please take one green thing. So you are familiar with this style. By the end of semester, everyone writes a little chapter or brief report. It's a very nice tool around, and there is a way to show a wave before because of several reflections. Okay. I'll bring next time. I may bring. Here are the books that may help you to feel comfortable in the course, but there are no required books. There are some manuals, there are some books, but we will do special path. So we are not going to meticulously go over all the chapters of standard books. We are not going to go over just technician manual for operating software. We will make a healthy blend of the cover. Yes, please.
Out of the 3, what is your favorite text?
Neither one.
And I kind of suspected. I have the green one.
Well, this one is not computational chemistry. It's quantum physical chemistry, but it has really nice overview of most of things that we do here, and it is short, since it is not main scope of the book. It overviews everything we do in class in maybe like half page per each lecture, or even shorter. So it's a good summary. So here's the list of subjects. We may adjust them as we go, but approximately we will follow them. So, and I also owe you to distribute syllabus, but it will have the same thing. So there will be 4 chapters, and approximately at the end of each chapter there will be a lecture when I will sit and relax and you will present, splitting lecture time on amount of participants of the class. So the first chapter will do this general background, like what is molecule, practical skills of building molecules, because without building a model you cannot characterize it. You know, like in wet chemistry there is a synthesis and characterization. By analogy, this one will be synthesis and this 3 will be characterization. During the first chapter, we will also look on the background for so-called molecular dynamics force field, so-called optimization of geometry, dealing with positions of atoms. While for the rest of the chapters, we will look on electronic structure. So, and there are people who deal with electronic structure methods for the whole life. We do not have so much time. We will focus on very selected topics, starting probably from the simplest and going a little bit up. So the simplest working electronic structure theory is so-called Hartree-Fock theory, which is not helpful for any practical calculations, but it is really good to send up a mind. It is a demonstration example how electronic structure theories are working and how they are programmed into algorithms and how they can generate typical styles of output, like energies, orbitals. During the first 2 chapters, we will cover software building models like Avogadro and Gaussian through Gauss view, and we will do some basic electronic structure and present it at the end of the second chapter. Then for the second 2 chapters, we will go into, so this is so-called density functional theory, which is a match of numerical cost and precision. It's not super precise, but it is very affordable to run by anyone, by every computer, at least for small molecules, and majority of publications are done with this workhorse. So we will switch from from Gaussian software to WASP software, and by the end of the second chapter, we will split practical skills between participants, and you will teach each other. Like one person will present one subject, another one, going over what we did in the labs. And for last part, we will go over background for describing excited states, which needs special theories, and we will focus on the research projects in parallel with the theory. So it's some of you are already exposed to some practical computations, and neither one of the words that I pronounced is new. Like Hartree-Fock, DFT, and TT-DFT is something that you're familiar with. Some of you familiar with. I do not promise, but I do have intentions to put links to recordings at the end of each chapter, so that if by some reason you are missing, you can watch it later. Let's see if the answer is working. So basically, it is a syllabus. What you will do. So during the first chapter, we will have labs, and some of you are already really experienced Linux guru. Some of you are not yet. So we will practice a way to communicate with modern computational systems, which are not Microsoft Windows nor Mac OS. It's a different environment, so-called Linux. And there are ways to launch massive jobs on massive computers, so you'll get some basics of it. I know that some of you are already experienced in this, but then you can assist others in the class. Building models, optimizing. If you have time, we can also include into the first chapters the transition states, search and normal modes, but it will be like icing on a cake if time allows. Then there will be a minimal standard set of skills for plotting density of states and orbitals. That is really simple, but it is a good complement to any research work that you are doing, no matter which area. And then there will be analysis of charge transfer state, molecular dynamics at ab initio level, which allows for bond breaking information and chemical reactions. And the following subject is not the biggest one in science, but I give it biggest value: creating movies, creating scientific animations of molecular dynamics, which is really helpful in analyzing what is going on in real world when everything, except very few experiments, everything happens at elevated temperature when ions are not sitting at specific places, right? They depart from equilibrium. And again, it's another icing on the cake. Maybe we will go through relaxation dynamics and lifetime photoexcitations, which are advanced topics, and I do not guarantee that we will have time, but maybe, and some of you may need it. So some of you are interested in making connection between structure and properties, right? And there are a set of properties like band gap energy, color, UV spectrum, lifetimes, how soon it will emit or relax, ability to form charge transfer, ability for like activation energy for specific reaction. So we'll try to cover these aspects. And if this chemical language is a little bird's language, we will cover the basics at the beginning of each class. So, huh? To my best understanding, because I do not have chemistry background. All my degrees are in physics, so there is a guarantee that we will not go too far into chemistry. Well, probably we will not practice too much of teamwork because the class is not overpopulated. If it will be more than 10 people, we would split everyone in groups of 2 to give presentations, not very short, but right now we have availability for giving individual presentations and writing individual chapters. Technical writing, you saw it. Peer reviewing, it means before we will make this skill, before we will publish these booklets, the chapters will go to you guys as to reviewers, and you will have chance to say how much you like writing of your peers, or opposite. And presentations, and then the movies, that scientific animations, will be published on YouTube, and then you will collect hits and likes.
Subscribers.
One of the persons who took this class from me at the first time I taught it overcame me in number of views, likes, and hits. Well, for scientific animations you can get millions, right? But he got 5,000 for one of the scientific animations he did in the class. He's so efficient that I decided to keep him with me for a longer time, and he's now postdoc more. So you cannot live so efficient people. 1, 2, 3, 4, 5, 6, 7, 8. Let's fill this. Let's fill this thing by coming. Well, I'll try to verbalize it, and then probably everyone will come and leave a little signature here. So, if you are taking notes, you may try to draw these boxes and try to fill them. So here we are trying to make flow chart of everything that is going on in this course, in the computational chemistry area, before getting into depth of the skills and procedures. So at the beginning, we are, maybe I will bring this time for ask you for help if I really need it. Maybe we will do it together next time. So initially, one starts with atomic models. At the end, one is getting properties. So, structure to property relations. So, some of you are from the research group dealing with cheminformatics, and structure to property relation, or quantitative structure to property relation, is your favorite abbreviation, QSAR. We are not making focus on how to analyze these relations. We are making focus on how to get at least few data points for these relations. So the models are things like that, right? Which you just record each model as a set of Cartesian coordinates, or so-called Z matrix, in the computer file. Properties will be like gap, color, like as we list. So what connects structure to property? Any ideas?
Hamiltonian.
Not bad. But let's look on this as users. Not as like big theorists, but like when we come to when we shop for something. We are not interested in a structure. What stays, what connects, what converts structure into property?
You have to optimize.
You're still too smart, too professional. Let's be really simple.
Okay.
Since it is computational chemistry, there should be a computer.
Yes.
Good. So, what is a computer? What are, like, philosophically? Two main components. Do not tell display and keyboard. A little more philosophically. What is a computer?
It does work.
Well, it's a way, like, to have a discussion. Yeah, but it consumes electricity.
Yeah.
But what computer is composed of philosophically?
Information.
Right.
Good, very good. What else?
Processing.
Processing. Any other?
Converting
Converting what into what?
one piece of information to another.
Information into data.
Good. Huh?
Information into data, or data into information.
Yes. So you're doing excellent, but right now we are looking on the two arrows which come in and out. You have some information in and some information out, but you see there are some blocks, two blocks. So if you take a screwdriver and start to unscrew computer, what we will see?
CPU.
Just like, yeah, motherboard, CPU, hard drive, or solid state drive. which are, what is a single word for all of this?
Hardware.
Yes, hardware. But is it sufficient to have best possible motherboard, CPU? What else is needed?
Software.
Yes, perfect. See, I told you it would be an easy course. Okay, now, which software is needed for computational chemistry?
Gaussian.
Well, computational chemistry
Yeah.
software, right?
Yeah, computational.
It's good. So, how do we decide which software we need for this computational chemistry stuff? Who writes the software for us, or how do we write the software if you really want to do it? What do we need to do the software?
Theory.
Perfect. Now, you're a mind reader. You got my style of thinking. Theory. And one can put like Hamiltonian that you mentioned at first. H psi equals E psi, right? So in some sense, here is our computational chemistry. Theory, software, on some hardware. We start with structures, we get properties. And on the labs, we will cover bigger part, and labs take smaller fraction of time. And with the lectures, which take a little longer time, we will cover theories behind the software. Okay? Yeah, it was too easy task to invite anyone to write it. I'll wait until there will be something more complicated and ask you to help. So, computer, software, hardware, models, properties or observables, and the theory. Right. One can add another box into this flowchart: comparison to experiment, scientific communications, getting appreciation from college. Right. I don't know what I'm going to tell you. Probably you already have a strategy. You just get through theories, look for software that implements them. But let's discuss. Well, we are going to describe molecules, or maybe very big molecules, which are like solids. By the way, this is silicon nanorod that Nathan is modeling with p doping and n doping. So it's your model.
There's leads on mine too.
Huh?
There's leads on mine too, though.
Yes, you will explain how to attach them during the course. So we are dealing with small or big molecules, right? So what is a molecule?
Combination of atoms.
What is atom?
Oh, you want to go that far? Okay. We're determining it's an element relative to like what the energy it provides, isn't it? Dealing with like, and you could go deeper and say it's dealing with what string theory in a way, because obviously once you go
Is it what,
further than an atom,
what you've got in your middle school or high school? Well, a little simpler.
Basic unit.
Huh?
Basic unit of compound.
What atom is composed of?
Electrons, neutrons.
Electrons and nuclei. We don't need to get deeper.
okay.
So there are nuclei which are either have different mass and charge, and we do have electrons, which always have the same charge and mass, but there is different number of electrons, right? Probably that's the main message for today's meeting. I don't know if I can get into more details. Okay, collection of yeah. I was supposed to draw it, but I have it drawn from previous years. Collection of electrons and nucleus, and if we are thinking at a level of freshman chemistry, we just count charge, mass, bonds, characterize which type of chemical is it? Is it like oxidizer or reducing agent? Is it organic, inorganic? But if we start thinking as a physicist, so you have collection of electrons and nuclei, and you want to bring some characterization of this system of nuclei and electrons. If you want to,
Charge spheres.
good, but the idea that we want to quantify everything, right? So how do we quantify? Like if you have something, benzene molecule, 6 carbons, 6 hydrogens, and you want to quantify the structure before getting properties. What do we need? What if we want to draw a structure like this in a computer? We're not going to paint, or we're not going to make lines in the PowerPoint.
Bonds.
Huh?
The bonds.
Bonds, but what bonds can be shorter or longer?
Coordinates of each of the atoms? Coordinates of the atoms?
Yes, we need coordinates. Simplest way is Cartesian coordinates. Sometimes there are crazy systems when there is a set of interatomic bonds. So we need a list of all nuclei, mass, charge, and 3 Cartesian projections. You don't have enough fingers. 3 projections. If I haven't taken quantum theory for myself, I may also set up 3 Cartesian coordinates for electrons, which is philosophically not bad, but later on through quantum theory we know that it doesn't have much sense because electrons are smeared out everywhere. But philosophically, if we have like benzene is too complicated. I'm tired of it. H2 molecule. We have 2 protons and 2 electrons. And we need Cartesian projections for each of these 4 particles, right? Let's do it. So if you are taking notes, please try to do it. And if you are, I'll skip it. If you are not taking notes, then maybe you will help me here. So we are trying to answer on a question, what is a molecule? So our goal is to quantify, to convert from structure to properties. And we agree the molecule is a collection of positive nucleus and negative electrons. If you want to set up Cartesian coordinates for each of the particles, what do we need? Like if we are taking geometry in a high school.
You need the x, y, and z coordinate.
Which start from?
The origin.
Origin. So we need to select an origin, right? Sometimes we can fit origin to center of mass or to one of the atoms, or we can take it arbitrarily, but we need to start from the origin. Okay, so this system has ways to have color coding. So let's put blue electrons, electron number 1, electron number 2, and red this is a really nice task to ask someone to help, but I like it so much that I prefer to do it myself. And it is easy enough. When there will be a hard task, I will give up and let you guys do it. So, and we have positive nuclei 1, nuclei 2. Right? And this is our origin. So if we want to set up, to quantify, so this is a H2 molecule. Right? And we are not yet determining exact answers. We just want to set up notations. Later on, we will feed these notations, these variables with some realistic values. But we need to set up a system of notations and agree on that, because otherwise it will be no reason to go further. So let me use lowercase vectors for electrons and uppercase vectors for nuclei. R1, R2, right, for electrons. And for nuclei, will be R capital 1, R capital 2. Good. So each vector are 3 components, 4 vectors, 12 components. Right? So to some extent, it is a molecule of it is a model of hydrogen molecule. Good. I'm going to scroll back a couple of slides because we need to agree what are we going to do with Cartesian coordinates. Right now, suddenly, we need to remember that once upon a time we took quantum mechanics a little bit. If you didn't, it's my task to make a little refresher. So the challenge and difficulty in connecting structure to property for molecules is that it is not just point charges that have forces. The classical mechanics is not sufficient to predict properties of molecules. We need quantum properties of electrons, which are moving so quick that they are distributed objects, right? And there is a specific theory, so-called quantum mechanics, to describe that, right? So who is very happy, exposed, and familiar with things of quantum theory? Who has never heard about it and feel very uncomfortable? Who is so? Okay, so I'll cover something, but just giving warning that I'm scrolling back in slides. So I'm going to make oversimplified, not true quantum theory, not everything, but really minimal basics. So if we do have one electron, it is being attracted to negative electron, is being attracted to positive ions, right? So it moves in a potential. When it is close, it is energetically more favorable. When it is far, it is energetically less favorable. In addition, electron can have velocity or momentum and kinetic energy. Okay? So if we are interested in energy of electron, we need to add together its potential energy and kinetic, right? On one hand. On another hand, we have heard it from the media. It's not a novel discovery that electrons are described not by where they are at this point of time, but as a distribution. And for these distributions, we need an equation. that will give this distribution and energy of such distribution. So there are following components. So one needs potential energy, one needs kinetic energy, it's called letter V, letter T, and then one combines them together, T plus V, into total energy, which is by agreement is denoted with letter H. Total energy. And we will go into details. We're just going through very simple overview. So for electron we have potential energy, which depends on position, kinetic energy, which depends on velocity, and add them together. And then when all of us were in middle and high school, we had a little of physics, right? Because in previous class, I had a person who never had physics at all. So if we are thinking on a language of classical physics, right, the position and velocity are variables. You can assign a value for it, right? Which is not quite right for quantum particles, for electrons that are so small, so quick. Instead of variable that has a certain value, it is so-called, what's the right word? Starts with letter O.
Oh, operator?
Yes, operator. So I need to list several concepts and then merge them together. So position and velocity are not point values but operators on one hand. On the other hand, electrons are not like stuff that's placed somewhere, but distributed everywhere in space. It's like a field, a function of 3 coordinates, or if it is more than one particle, more coordinates, right? So there are operators, and there are so-called wave functions. Wave functions, which are x, y, and z, functions of 3 coordinates, or vector. So there are very simple, I will show them in a minute, ways, there are simple expressions, how to express kinetic and potential energy operators. But now I'm trying to bring things together. The life goal of operators, their destiny, is to act on wave functions. So operators always stand in front of wave functions and they change them. So operators are like taking derivative, most typical derivative. Derivative changes function. So, position, momentum, potential energy, kinetic energy, Hamiltonian. All of them act on wave function. And now the main part of the super simplified quantum theory. If we are able to formulate Hamiltonian operator in the right way, I'm not showing it explicitly how, but if we are able to write differential operator for Hamiltonian, then we can write equation that Hamiltonian operator acts on the wave function, and then it generates wave function again with some energy. Here we put index I. I'm not having speech defect. I'm just repeating this I several times, which depends on position here. So, so Hamiltonian will be known, and the wave function and energy will be unknown, but you don't hide. Maybe this one will. So if we are able to formulate Hamiltonian, then we need someone who will solve this equation for us. If we are in the integrated quantum theory and we have only one electron, we can solve by ourselves for simplest cases, like particle in the box. Right? If it is truly multi-electron big systems, we need computers. But everything what we do, not everything, but substantial part, will be connected to solving of this equation. So first, formulating Hamiltonian, so letter H, and then, so see it is one known and two unknowns, but it is possible to solve such equation. So this equation will have several solutions, but orbitals, these psi functions, will be shapes how electrons are distributed in space, and energies, what will be the energy of each electronic orbital. Okay?
What is after the psi? Like I can't. Is that a?
It's my absolutely perfect calligraphic R.
Oh, okay. All right.
Sorry for.
No, it's okay.
Are you sure?
Am I sure about what?
Okay.
I see. Okay.
And then that's
Okay.
equals.
H times psi as function of R
Yep.
equals
Oh.
E times psi as function of R. And both psi and E do have index I.
What is
Because this is very shorthand notation for equation in partial derivatives. And equations in partial derivatives typically have more than one solution. So each solution is labeled by index I, running over 1, 2, 3.
So psi is unknown.
It is unknown before we. Yes, it is unknown that we need to find.
Okay.
And in narrow sense, computational chemistry is a science of solving this equation for big molecules. It's not absolutely correct. There are some additions, but in narrow sense, what we're doing is formulating atomic structures and finding these psi wave functions.
What's E and R on that equation?
Where?
You said E, you said E and then R.
R is
I know.
position in space. E is energy. Do you permit me to go forward? Or you want me to mumble more about the previous one? You're not yet tired? Or you're always tired?
We have to get used to it.
Okay, so a little thing. If it is your first exposure to quantum theory, you may lean back and relax for a couple of minutes. I'm going to tell something not super complicated, but a little bit more advanced. If you miss it, you will not miss. You'll survive the course anyway. But what we have seen before this H psi equals E psi is time-independent Schrödinger equation. Schrödinger is a famous guy who designed this equation. Time-independent because there is no time there. Energy, position, Hamiltonian, everything is time-independent. But in fact, in real life, in real nature, everything is time-dependent. And Schrödinger was not so silly to forget about it. It's just time-independent is more simple and more important to try to solve at first hand. But there is a little extension, and originally Schrödinger equation means time-dependent one. So here is the time-dependent. You apply Hamiltonian to a known psi function, and it gives you how psi function changes in time. So time derivative of psi equals h bar psi. And from this time dependent, one can derive time independent. And if you do know, if you were so lucky that you have solved time-independent Schrödinger equation on the previous slide, then you are rich. You do have, you do have set of energies, and you do have set of psi functions, right? So if you, it's a lot of information, and we will computationally learn how to collect them. So if you do have set of psi functions and energies, one can construct time-dependent wave function, which, because this electronic clouds may change in time if someone kicks them, perturbs with light, or if molecules collide in chemical reactions. It is also needed. So psi times exponential with imaginary unit and energy and time, and then each wave function is multiplied by expansion coefficient. And then it will be a wave function that will be like dancing with time. It's a just little note that limitations. Time-independent Schrödinger equation is not the whole story. You need some time. There is a way to include time dependence.
Is there something after the T? Because it looks like it's covered up by the little pin.
Yes. Guess what? I'm confident that at least one person in the class knows and can answer this question even if walked up in the middle of the night, and I have a suspicion that few more people have guessed. So let's discuss what is hidden under little pen.
X.
Huh?
No.
X.
Good try. Other options?
Constant, maybe?
Which constant?
A? No. You...
X.
This symbol is already presented in.
Oh, the coefficient, that one, the blue one.
No.
No?
H bar.
What is H bar?
The Planck's constant?
Yes.
Oh!
You know what is Planck constant?
Yes.
Okay. So it comes up here, and it comes up here in the denominator. So dimensionality of Planck constant is same as angular momentum or as energy times time. And if you multiply energy times time and divide by Planck constant, which is not seen here, then you have dimensionless power of exponential, and it will accumulate phase. Thank you, Gage. I'm proud of you.
So I remembered something.
The blue stuff.
Oh, this expansion coefficients.
So is it like, do you have like a parenthesis there?
No, it's just a big C.
Oh, okay.
Last year, I was inviting volunteers from the class, and they did it in layers. First did the whole equation, and then I told like, hey, you have forgotten the C.
Isn't it supposed to be plus C?
No.
Just kidding.
And there is an equation how to connect initial shape of wave function with C coefficients. Just overlapping,
Okay.
right? Initial state with later.
Okay.
And some of you may recognize this slide because I borrowed it from instructor who taught this course at this university 5 years ago. It's a summary of the same thing. Like time-independent Schrödinger equation, set of psi functions and energies, time-dependent and expansion. But we already got it. What is new here is explicit shape of kinetic energy and potential energy, which probably we need to cover. We're already here. So I'll write on a side.
You should forgive me for my issues with the notation, but isn't it saying it's a function of x and t? So you're saying it's time independent, but yet it's a function of time, that phi on that.
This is time dependent.
Yeah, but then the line literally says the time independent equation. If you look to go above, it's further
No,
up.
at the top, the circled one, right?
Yeah, right there. Yeah, time independent equation, and it's saying phi is a function of x and time. So I'm just curious.
This is wrong.
Okay.
Thank you
Good
for
catch.
the good eye.
I was like, what?
Excellent. We will have the slides will become perfect with years. Thank you. So let's recall who we are, what we are doing, what are our goals, and how close we are to reaching them. So we need to establish structure to property relations. We have an idea how to quantify molecule as a set of Cartesian coordinates, and we know that electrons are distributed in space, and we need to solve Schrödinger equation for electrons. So we do need explicit expression for Hamiltonian operator. We do need to write down what H is, right? So how do we write what H is? H is kinetic energy plus potential energy, right? For kinetic energy, we need momentum of each particle in the system. For potential energy, we need position of each particle in the system. By some reason, in each class, upper right side of touch screen is not writable. So kinetic will be P squared over 2m, right? You recognize this equation, which is the same as mv squared mv squared over 2. So this equation doesn't surprise you, right? Mass times velocity squared over 2. And since m times v is p, we can go from this notation to this one equivalently. And potential needs a little refresher of electrostatic and Coulomb's law. Who has never heard about Coulomb's law? Who is able to go to the blackboard and write down Coulomb's law? Okay, at least one. Anyone else?
Ohm's law, no?
No, not Ohm's. Not Ohm's. Coulomb's.
law.
Not comfortable. Who can do it with a little help, or has general idea what is Coulomb's law? Do not hesitate. It's your grades will be based on research, not on the knowledge.
I haven't seen that equation in like 5 years.
But
That law.
what does it connect?
I have no idea. I just know of it.
Any ideas? Because if I declare it, you will forget it quickly. If you discuss, it will be better in our memories.
Well, it has to do with part of what you just showed us up there, right?
Yes, everything is connected.
Okay.
So why electrons do not depart from nuclei?
The charge.
Electron charge.
Which force brings them together?
The charge of
Electromagnetic.
Electrostatic.
So electrostatic force that brings negative opposite charges together in the smart colloquial language is Coulomb's law. Okay? So if someone will torture you on your thesis defense, you can at least say this one. Hopefully you can provide something better. So if you do have charge 1, charge 2, and distance, will like R1 minus R2 with some constant. So it will be V as function of R1 and R2. charge and distance between them. If they're really close to each other, if the positions of two charges, of 2-point charges, are very near each other, then they will interact like crazy. If they are far away from each other, if this R1 minus R2 is infinity, then Coulomb's law is 0, gives you 0. Okay?
That's absolute. R1 minus R2?
Yes, yes,
Okay.
absolutely. So if there are two charges of the same sign, it will be repulsion. Positive energy means things are repellent. If energy is negative, if so it stabilizes system, it attracts. So it's important that charges Q1, Q2 will be opposite. So multiplication of charges, subtraction of distances. Now you have solid background in classical scientific education. Good. So, and these two things, kinetic and potential energy, enter into Hamiltonian. That we need to, I hope that we'll have enough steam to complete it today.
Will you also share the notes?
I already did.
Oh, okay. No. I meant the completed notes. Or just the video lectures, which...
I don't mind sharing them.
Okay, that'd be great.
Yep. Do whatever is comfortable for you, but I recommend, well, maybe if I would be taking this course very seriously, I would, like, as a student, I would print notes before and fill them. But I'm not sure if you plan to do so, therefore I'm not printing it for everyone.
No, I mean, like, yeah.
And you can relax and wait until notes are coming, but it's my personal experience from undergraduate time. When I'm writing something, it scratches through the memory and memorizes much better than...
Okay, sounds good.
What did you say about the equation up there?
This one?
Yeah.
This is kinetic, this is potential.
Okay, so that's a breakdown.
But here it doesn't specify what is V. It tells a little bit more what is kinetic, it's second derivative or position, but I'll go over it a little very soon. Okay. So going back to my favorite figure. So for kinetic energy, it will be really easy. It will be a lot of very boring writing. And it is one of the reasons why it is much more pleasant to be computational scientist rather than theoretical. You do not need to write much. And if you do theory, you derive equations through several pages. So for kinetic energy, it will be simple. But for potential, we need to carefully take into account all pairwise interactions. So by now, you do know that Coulomb's law involves 2-point charges. And we do have 4. Right? So you need to consider these 4 charges as pairs. How many pairs? 1, 2, 3, 4, 5, 6. Right? And each of them will give contribution to potential energy. Right? And you have noted that there is an absolute value of the distance. Right? So we need 6 absolute values, 6 distances. Let's carefully draw them here. So here this one will be R capital 1 minus R capital 2 this one will be R lowercase 1 minus R lowercase 2. I was wrong. It should go, arrow should go only one way. It is a vector. I didn't put absolute yet. So this one will be R1 capital minus R1 lowercase. This one will be R2 uppercase minus R2 lowercase.
Do you have those backwards? Or do you have like the first set you did backwards?
We will.
Yeah, I mean
Yeah,
it doesn't matter.
yeah.
But
I just have a problem that if I keep this highlighting color, it will be not visible. Maybe I'll do thin. R1 capital minus R2 lowercase and R2 capital minus R1 lowercase. If you draw it yourself, maybe you'll be more artistic and more comprehensive. So these 6 distances are needed to formulate Hamiltonian, and we need Hamiltonian to find electronic orbitals to solve for quantum states. So, how many attractive parts are attractive terms will be here?
4.
1, correct. How many repulsive terms?
Same.
Huh? 2. Yep. 1 for
Oh, yeah.
between 2 nuclei and 1 between 2 electrons. Okay. So if I do want to write at least potential energy, I need to write down 6 times Coulomb's law, right? 6 terms. And for electrons, just for the future, we have mass. Oh, I want to tell you a secret. Do you like conversion of units? Does anyone like conversion of units? What are atomic units? Raise hands if you heard about them. Raise hands if you have never heard about them. Give sign if you are so-so. Okay, so conversion of units is a way to torture young minds in school and college. True scientists do not bother themselves with this stupid thing. There is a system of units where all constant, most of the constants are equal 1, and one just skip them. Right? So remember when we wrote Coulomb's law, we put this coefficient, which in fact in SI unit it is 1 over 4 pi dielectric constant of vacuum. If you're in atomic unit, you just skip it. If you need to deal with mass of electron, you need to memorize how small it is. But if you're in atomic units, it is 1. Planck constant. It is like 6 times 10 minus 34th, like joules times second. Very ugly. If you're in atomic units, it's just 1. Right? So if you agree to do everything in atomic units, our life will be like a piece of cake.
You do electron volts.
We convert only from atomic units to electron volts, or whatever nanometers what we need in communicating our computed results with experiment. And it will make less strain on a hand while repeating writing Coulomb's law again and again. So we can write that there is a charge of electron, but it will be actually 1. And position R1, R2. Momentum, we can call it P1, P2 vectors. And for nucleus, we can call it as capital M. Charge, it will be, well, it will be different. So sometimes it can differ from 1. Position R1, R2. Momentum P1, P2, just using uppercase. And for Coulomb, for potential energy, we can carefully add together plus, and I'm working in atomic system of units. Position of nuclei 1 minus position of nuclei 2, absolute value. Repulsive, positive. Positive energy is bad, means like hating each other. Plus, and I put here 1 instead of charge of ion because protons are so easy, they have charge 1, same as electrons. I intentionally selected this example. So plus 1 over R1 lowercase, R2 lowercase. So it's again a term of hating. 2 electrons hate each other and try to depart from each other. 2, repulsive. And then minus 1 over R capital 1 minus R lowercase 1. So it's attraction of electron to its own personal nuclei minus attraction of the same electron R1 to a foreign ion, right? Minus 1 over R capital 2 minus R lowercase 2, attraction to its personal host nuclei, and minus one more term R1 minus R2. Like I'm walking with a dog, and dog, instead of coming to me, coming to another person. Okay. It's attracting to foreign side. 4 terms. So by now we are so rich. We already have half of Hamiltonian. You never thought that having so many terms in Hamiltonian it means to be rich. So we do have 6 terms, potential energy for Hamiltonian. Now we need to add kinetic energy and we will be done. So this potential is not one dimensional. It is how many dimensional? 12? 4 more, right?
Because one has 3.
Each has 3. So it's easy for us to, by human abilities, to imagine one-dimensional potential or two-dimensional potential. But if you even 3-dimensional with color codes. But if it is 12-dimensional, it's a little uncomfortable. But with equation, it's fine, right? So moving in 12-dimensional potential. So I promised you that kinetic energy will be simple. I'm trying to rewrite this, redraw this equation each year, but it seems that my drawing skills becoming worse and worse. So I think we are already approaching the threshold of human abilities. We need to wrap up soon. So probably when we will be done with kinetic energy, we will leave anything left for another meeting. What is here on the top? Who likes this equation or who hates this equation? You can show like, or if you okay. any other votes? Would anyone be able to explain what is this circled equation?
the momentum operator?
So remember we were talking about that in classical mechanics, momentum is a variable with a single value. But in quantum theory, it is a differential operator that acts on the psi function. And this is very simple. It is the simplest operator that is easy to memorize. You see, it is for one-dimensional projection of momentum onto x dimension. It is do dx, derivative, first derivative, and it's multiplied by minus imaginary unit and h bar. Right? What is kinetic energy?
It's the energy of the electron.
Right, and mathematically it's p squared over 2m. Right? So if one plugs in this stuff into p squared, px squared over 2m, one would get minus h bar squared over 2m d2 dx squared, right? Because we have kinetic energy is momentum squared. From first derivative we get second derivative.
So we just literally plot that into for the momentum.
Into kinetic energy, yes. And for now we can skip this little translation from classical to quantum because it is obvious. We need nomenclature to count terms. So one more thing that doesn't have much science behind, but as quantum accountants, we need to have different rubrics for each stuff to have it organized. You already realized that there are many terms. Of course, we are going to run software. We are never going to derive equations for bread and butter, but just to get through, it would be reasonable to separate terms in the Hamiltonian and speak of them separately. You already noticed that there were there were 6 terms, and they were broken onto 3 groups. Potential energy of interacting of nuclei to nuclei. Potential energy of interacting electron to electron. And potential energy of interacting nuclei to electron. For hydrogen molecule, it was really quick and easy, right? But if you need benzene molecule, it will be a huge amount of terms. I'm not sure if you really want to write them down, but at least we can tell for sure there will be 3 types of terms. I can quickly write them here. Plus 1 over R1 minus R2 plus 1 over R lowercase minus R2 lowercase minus 1 over R1 R1 minus R1 R2 minus 1 R2 R2 minus 1 over R2 R1. And how many, in the same way, you can count terms for kinetic energy. So there will be kinetic energy of nucleus, N capital, and kinetic energy of electrons, E lowercase. How many terms for nuclear kinetic energy? There are 2 nuclei. 1 term per each if we are in vector form, or 3 terms per each if we are writing components, which we are not going to do. So, shorthand, P capital square vector 1 over 2 m mass of probe plus P capital vector square 2 divided by 2m. And for electrons it will be P lowercase 1 square 2 mass of electrons plus P2 squared over 2m. So we, at this time, if I would be sitting on the other side of the barricade, I could be scared away, thinking that, oh, if you are going to write such Hamiltonians each time, I don't like this course. No, we are not going to. We are going to write some equations, but in our practical work, we are not going to derive equations. It's just understanding what is implemented in the computer code.
I have a question.
Yes,
The
please.
screen is covering up so it's 1 over big R2
Yes.
over
Yeah.
R minus, and
Yeah.
then the next one's gonna be big R2 over little R1?
Yes.
Okay, got it. Or minus R1, okay.
I need to memorize, not to write in the lower left corner. Okay. So how many terms total? 4 plus 6. 10 terms in the Hamiltonian, right? So we put big brackets, 10 terms in there, acting on the unknown wave function. And to be with an independent algebraic equation. If I'm lazy to repeat the same equation 4 times, I can implement notation for summation. Right? If I want to use this kinetic energy of nuclei with index I that runs from 1 to 2, kinetic energy of energy with momentum of electron with index lowercase I running from 1 to 2. And here there is no summation here for 4 times, so we have I capital running from 1 to 2, I lowercase from 1 to 2, and here R lowercase I lowercase minus R uppercase I uppercase, right? Adding together all terms. And this is our Hamiltonian. Good? So I think this form is something that we can digest instead of writing this explicit form. Just understanding the terms T and V, N and E for kinetic and N, E, and E. So how are we going to call this beast? Of course it is Hamiltonian, but it is not a Hamiltonian for one electron. It's not a Hamiltonian for one proton. It's a Hamiltonian for the whole molecule. So it is molecular Hamiltonian. So if we are putting if we act with this unknown wave function onto, with this molecular Hamiltonian onto unknown wave function, we are doing absolutely correct but absolutely useless thing. It is general equation where both electrons and nuclei are considered at quantum level, right? And you know that nuclei have some quantum properties, but they are not so important. So we are making general but too rigorous. So we will discuss this equation today, maybe on Tuesday, but then we will make anything we can to simplify it. Even for H2 molecule it is complicated, but for anything realistic it is unsolvable and unpublishable if you do some research with it. But we need it as a background for all our theories. So what, it's definitely ugly. Why? Because it depends on several R sub I positions of nuclei and several positions of electrons.
So basically, it's like if you try to describe this system.
So it's about 100 ions times 3. It will be 300 projections of Cartesian coordinates for nucleus, and silicon has about 20 electrons times 100 times 3, and it will be just number of independent variables. So it's just a mathematically abstract model. But formally, if maybe with advent of quantum computers, one will be able to solve such equations in small cases. But in this course, we will try to find approximations and ways to simplify this molecular Schrödinger equation. It's time independent and this molecular Schrödinger equation because it includes everything in the molecule. I'll cover the things later. I think it is enough. Right? You need to digest it. So, a little organizational note. I'll chat personally with Gage if you vote to start Thursday meeting maybe 15 minutes later, or we can still plan on 6 but arrive with delay. I can easily or agree. You have time, about a week to tell you your decision. And for Tuesdays, we can either keep this room, but then we will be kicked out after 1 hour, something like this, which maybe you like, that
Yeah.
a little pressure. Or we can do Tuesday meetings in the same room where the labs, which also has recording facilities and big screen. So,
I'm indifferent to either one.
okay, then I'll meditate during the weekend. And
I guess in the lab, so we don't have to do them all.
if you will do everything in the lab, then all 3 meetings will be in one.
Yeah, that'd be nice.
Probably we can do even Thursday in the lab. And for Gage, it will be quicker to go from Morrill Hall to QBB.
Yeah. So 400, that room 400 and
132. 400 is available on the mornings.
Oh, okay. The
On
130,
evenings,
got it.
there are, it's overbooked.
Oh, okay.
But the lab is available. Done?
Yes.
I'll stay here to answer any questions, but formal meeting is done. Everyone is welcome to meet.
So are you gonna post like lecture and the slides that you've written on just now? Like you just had slides that you modified right now. You're gonna post those?
I will send it as an email to everyone.
Oh, I haven't checked. And
And link to.
Okay, perfect.
I'm not sure if I was supposed to.
So
say something like-
are you on Blackboard as well? Did you put them on Blackboard?
I assume that I should be literally but I'm not.
Okay, because
It's above my intellectual.
I am registered for the class, so I am definitely, I should be in there, because I
But
was,
I'll try to communicate in the.
Seems like someone very happy.
okay, perfect.
I'll do those.
Oh my god.
Computer science down there is online and stuff.
Okay.
I know. That's why I slept in today. I'm like, I know today was gonna be